Hello, everyone. Welcome to this webinar, Beyond Model Monitoring and How to Monitor Machine Learning Features on Hopsworks. My name is Javier de la Rua Martinez. I'm a researcher engineer at Hopsworks and industrial PhD at KTH University in Stockholm. And yeah, I'm going to talk about how to go from monitoring your models to actually monitoring your features. So first of all, let's define what is a machine learning model. A model is like a function that is optimized to make predictions based on hidden patterns that we might find or not in a sample data. So from this data, we will split it into features, and we will identify the label that we want to predict. We will train a model on this data, and then we will use this model with unknown data to basically make predictions on these labels that we don't know the value of. But to better understand what are the problems or challenges with this, let's look at the following analogy. Every person have different physiques, so let's call these hidden patterns. A person might have myopia, hypermetropia, astigmatism, and so on. So you need, this person probably needs to go to the optician to evaluate the sight. So the optician will just readjust the lenses, ask you to read the characters, and then by doing that, generating this sample data with the label if it's readable or not. And at the end, you will come up with specific parameters with which you can build your lenses so you can see properly in the real world. But we can use this analogy also for the business data, in which these hidden patterns are located in your domain-specific data, and you basically want to train a model to optimize on these patterns, so you can use this model in your real-world scenario. But coming back to the analogy, once you have trained this model, there are several things that can go wrong. For example, this model may not work for a different use case because these hidden patterns are different, so it will not optimize well, or not, it will not predict properly. Also, if it's the same use case, you might find that over time, the hidden patterns might change. So, for example, one grow older, and at some point it will, the myopia, for example, can go worse. So you, at some point, you have to come back to the optician and just basically evaluate your sight again, readjust the lenses, and get a new pair of glasses with which you can see the real world. But even for the same use case and hidden patterns in your data, there are also some scenarios in the real world that might not be, the model might not be efficient for these specific cases. For example, we see in the picture, there is the sun like really bright, so you might need in this case sunglasses instead of a normal pair of glasses. So might not work for every case in the real world. And how can we monitor for these changes and how to resolve these problems? So in theory, there are multiple formulas. If we see this problem from a Bayesian perspective, there are, you can find in the internet a lot of concepts such as a concept shift, real concept shift, covariate shift, and different ways in which these patterns or this data might change. But this is hard, basically. And in practice, there are several approaches that we can do that are easier and are more straightforward and quite efficient in terms of monitoring your data and seeing if these patterns in the data can change. So, for example, as we can see in the tables, you will have different training data sets, inference data, and also outcomes that you might use later on to double check if your predictions were right. So you can compute the statistics on all this data and then compare the statistics to see if the data shift or not. So if we have a look at how model monitoring is seen in an simplistic view, we have, in this case, two different pipelines. The training pipeline, where you will have as input the training data set, train your model, which will be basically the output, and then an inference pipeline, where you will use this model on new model inputs to basically make predictions. So the traditional way that we see model monitoring here would be, I will take my predictions, model predictions. I will also take the training data set and the model inputs, and additionally, at some point, I might have the real outcomes or the real value that should have been predicted. I will take all of this and evaluate the performance of my model. But the models actually do not degrade over time, as it is mentioned several times, but instead, the data that is used for creating the training data set might change. The patterns that we saw before might change. Also, the model inputs might change. And in the end, also depending on the real use case, you might have different patterns that also might change. So at the end of the day, we can see this problem as a feature monitoring problem, basically. So we can, instead of monitoring our models, we can monitor the features that are used for the training data set, for the model inputs, and then also the labels from the predictions and the outcomes. And additionally to this oversimplistic view, the data can change as well in previous steps before the training data set, which are basically data collection, feature engineering. Then at some point you will polish your features to generate the training data sets. But in these previous steps, you might introduce also different changes that might affect the patterns on this data. So if we see this challenge in a more sophisticated way, in a more complex scenario, in this case, we will have 3 pipelines, which is a good practice for building machine learning systems. Additional to the 2 pipelines that I mentioned before, training and inference, we have here feature pipeline, which basically has as input the raw data, the new data that you will ingest into the system. And here is where you will basically engineer your features and prepare your features for future model training. And basically, these machine learning pipelines do not come alone. Basically, you need a data layer to store and manage all these features and the models that you will be dealing with and that will be shared across the different pipelines. So in Hopsworks, we provide different abstractions, such as feature group, which can be seen as a mutable table, where you will basically save your features that are already polished and created. And then we have also feature view, which is an abstraction that we use to define how you want to consume your features. So how you can basically select which features from different feature groups you want to consume to basically generate your training data, or also during the inference pipeline if you need to compute features on the fly. So in this scenario, there are multiple data transformations that can be applied at different points. So we see that we have, in this case, on-demand feature transformations, which are transformations that are that produce new features that will be either used later on to as part of the training data set, or and also will be needed to apply on model inputs to generate the features that will go into the model at prediction time. Then we have model independent and model dependent features. Model independent and model dependent transformations, which basically are feature transformations that model independent transformations basically do not depend on the model. So these features will be produced and stored in the feature groups for reuse and can be used in different training data sets. And then the model dependent transformations are transformations that are applied on features that will be directly used to train the model. So it basically depends on that model. So in this sophisticated scenario where we see different data transformations, there are several things that can go wrong here. So first of all, there might be code changes that can introduce undesired data changes in your features, and later on affecting the rest of the system. And also there can be data changes. So basically, we have a data change early in the first steps of the data flow, then these changes will be propagated until the end. You will see this ending up as, for example, degrading of the performance or predictions that are not correct, and so on. So basically, how can we analyze this data at different points, and how can we select the features that we want to compute the statistics on? So for that, one very useful tool is and really well known in data streaming is called the windows. So we have different types of windows here that we can see. We see on the left the static windows, which doesn't matter at which point in time is fixed. It will cover the same amount of feature data. Then we have expanding windows, which over time, it will basically expand the end of the window, but the origin or the start of the window will remain at the same point. And then we have here as well sliding windows, which basically both start and end will just slide or roll over time, covering different range of feature data. So given this type of windows, we can use them. We can use this classification to define two different windows: the detection window, that we will call it, and reference window. The detection window will basically define the boundaries of the feature data that you want to compute a statistic on, and this is the statistics that you will want to analyze and compare against a baseline. And then the reference window, which will define the boundaries of the feature data that you want to compare against. So then let's see how to set up feature monitoring using these windows that we just mentioned. The first step is basically compute the statistics on one or more features. For that, we have to define our detection window. There are different ways to do this. So if we see the blue color, this detection window will cover the whole data in the feature group that we saw in the diagram before, which is the place where all the feature data will be written or stored. So basically, in this case, it's a spanning window. This spanning window will cover from the origin of the feature group until the point that you basically the monitoring is happening. So all this feature data will use to compute the statistics. Then we see with red color a sliding window. You can specify, for example, that you just want to analyze or compute the statistics on the feature data that was ingested the last week. So from today that the monitoring is happening, you want to take the 1 week ago of data, of feature data, compute the statistics on, and analyze it. And then you can also compute the statistics on a specific commit. So data that was ingested at one point in time, And this is basically a window with length 1. So apart from that, once you define the detection window, you can specify when you want to basically analyze this feature data. So it can be on a schedule, if you want to do it, for example, on a daily or weekly basis. It can be event-based. So, for example, when I just ingest new feature data, I want to get this feature data and compute the statistics on it, or on demand, which is basically pressing a button that will trigger the statistic computation. So in Hopsworks, we provide a useful Python API to set up easily feature monitoring. As you can see here, we have FG, which is basically an object that represents our feature group, and we can call create the statistics monitoring to basically use the default parameters to compute the statistics on this feature group on a daily basis. But then apart from that, you have the job frequency parameter, where you can basically change the frequency when to compute the statistics. And also you can define more sophisticated detection windows, as we see in the third example, in which you can provide the time offset and also the window length. That's not here, but you can also provide it, and the percentage of feature data. So basically with the time offset and the window length, you can basically define your window at any point in the past. And you can say time offset 1 week is like starting from exactly 1 week ago, and then 1 week of window length, so it will cover the whole week until now. Right. Then the next step, after defining the detection window, we can optionally define a reference window. So if we don't define the reference window, then we will just compute over time statistics, so we can observe in the platform how the statistics of the feature data evolve, and we can see, we can use human intuition to detect anomalies in the blink of an eye. But if you want a bit more of automatic monitoring, you can define a reference window. The reference window, in the same way as with the detection window, can be, in this case, a static window, which is like a training data set. When we create a training data set, it's basically a snapshot of the feature that we have in different feature groups, and we use the feature view to basically select the features that are in the different feature groups. We read this data, and we generate a static set of data. So it's basically a static window. But then we have also the option to define a sliding window. I see here rolling, is rolling, sliding, the same in this case. So you can define also a sliding window that will be used as a reference. And also you can specify a fixed value, such as 123 or any other value to compare against. And then you can specify as well. So by default, all the descriptive statistics will be computed, like mean, max, mean, count, and standard deviation, and so on. So when you want to compare against a reference, you're going to specify as well which metric you want to target. If you want to, for example, if you specify a reference value, which is a fixed number, it will not be useful for all of the statistic metrics. You have to choose one. So you will say, for example, the mean, and then the mean will have as a reference 123. Then if you want to do this with Hopsworks Python API, it would look like the following. You have the method with the reference value that we can just provide a specific value that you want to compare with, or you can define the reference window in the same way as we did with the detection window, or you can specify the training data set that you want to compare statistics with. So if you specify the training data set, basically, Hopsworks knows the statistics that were computed when you generated the training data set. So it will automatically look for the specific statistic metric and compare against it. And then finally, when you define the reference window, you can just call compare on to specify the metric that you want to target. Then one step, the next step would be optionally to set up a threshold, which is basically a way of setting a boundary for anomalous values. So we can see in the example, there are three parameters that are related to this threshold. One is the threshold itself, the value, then a strict, which is basically if it's a strict comparison or not, and also relative, if it's, as we can see, relative mean or absolute mean, if it's a value that is relative to the statistic metric computed, or it is absolute. And then as well, optionally, so all these steps will add on top of each other, but you can just do the first one, which is basically define how you would want to compare statistics, or then set up the reference, then thresholds, and then the last one would be if you want to set up alerts. So you can, in Hopsworks, you can define different alert receivers, which would be, for example, an email or a Slack channel or a PagerDuty. And then you can define alerts at a feature group level or at project level, which in this case, as we can see, you can select as a trigger if shift was detected. So in this case, it's assumed that you specify a threshold and a reference window, and if this if the value difference is over this threshold, then it will trigger this alert, and it will send a message or email to the account that you specify in the receiver. So just as an overview of different use cases or common use cases that would be that in which feature monitoring will be used, is the first step would be, or the first use case would be the simplest one, which is basically observing statistics over time, as I mentioned before, just to trust on human intuition to identify these data anomalies. Then another use case would be if you want to compare data that is being ingested against a specific training data set. So in this case, for example, imagine that you basically, at some point, you train your models, you put them in production, but you keep inserting new data. This new data could be the inference log, as we saw in the or predictions log, as we saw in the diagram before. So you will ingest again these model inputs and predictions that we saw in production. We insert it into the feature store, and we want to compare these values against the training data set. So to see if, to detect at what point the data will shift, and this can be either bad or good. It depends how you see it, or depends how big is the change, because at some point you will want to retrain your model. So you can use this also as a way of deciding when you have to trigger another model retraining. The third use case would be basically compare the data that you are ingesting in the feature store with existing data that you have already to see if it differs. And the last one would be, I mentioned it before, compare the inference logs, basically. So let's have a look at sort demo that I have here. I hope you can see this. Okay. So this is Hopsworks. I defined a feature group from transactions. So this is a tutorial that we have available in Hopsworks. That's tutorials in GitHub, and it basically uses the use case of detecting fraud in credit card transactions. So in this case, I have a feature group with data about transactions that happen with an amount and a credit card number and so on. And in this feature group, I define different feature monitoring configurations, as we can see here. Let me go first to the notebook. I think it might be clearer here. So this is the notebook that I was mentioning before for feature monitoring. So first, I basically use the Hopsworks Python API to log in and get an instance of the feature store. I generate some data for the transactions. I create my feature group called trans.fg. And then later on, I also create the feature view and a training data set here. And then after that, I'm ready to start creating my feature monitoring configurations. So in this case, in the first one, we can see I just use the feature group to create the feature monitoring configuration with all the default parameters. In this case, just name and description. So in this case, we'll compute all the statistics on all the features of the feature group, not one specific, but all of them. And also on all the data in the feature group, because I didn't define yet a detection window. So it will mean like all data in the feature group. Then from the feature monitoring config object, we can directly change different values and save it just calling .save. I create here a second feature monitoring config, in this case, targeting a specific feature in the feature group. Then additionally, I created another one here defining the detection window, taking into account 1 week of data, but only 20% of the feature data that is in 1 week. From now and back in time. And then if we want to set different reference windows, I create an example of each of one. So the first one is comparing against a reference value. So with value 100, compare on the metric mean and uses the threshold 50. Then also you can detect, you can set another feature monitoring configuration for the comparing against a trending data set and so on. So basically you can configure as many feature monitoring configurations as you want per feature group, and it can be also on the same feature and targeting different statistic metric, or in the same feature group but targeting different features and so on. It's up to you, and it's depending on the use case as well. There are some features that are more or you expect more that they are more prone to change over time, or there are some features that are more have more impact on the models that are trained, for example. So you might prefer to just set up feature monitoring on those specific features. And then yeah, basically using the feature monitoring configuration object, you can call get history to see the different results that were generating every time that the monitoring was triggered. So, and also you can get all the configurations that we have for a specific feature group and for a specific feature view here. So these ones were the ones that I created. Actually, I didn't call this later on, so they are not deleted yet. So if we go back here to the UI, so as I said, I have here the transactions feature group, and every time that we create a feature monitoring configuration, a job will be created, and this job is attached to the specific feature monitoring configuration. So every job has a different schedule. As we can see here, this one, if it's green, means that it's enabled, so the schedule is active and it will be triggered at some point in the future. We can see here next execution time when will be, and also here a specific cron expression. And so basically every time that this schedule triggers the job, another execution of the feature monitoring setup will be triggered. So basically the data that is the feature data that is defined using these windows will be read, and then computing statistics on them, and then compare statistics depending on the configuration that we have. So these are jobs here. If we go back to the feature group, this is the feature group that we have with transactions. There is here a tab, feature monitoring. If we go here, we can see the different configurations that we were creating in the Jupyter Notebook. We have here configuration for all the features. We're using a detection window which is sliding or rolling with 1 week and of time offset and 1 week of length. Yeah, basically we have all the configurations that we had, and as we can see here, these two configurations were applied at feature group level, not specifying any feature, so it will be computed for all the features in the feature group, and these three will be just targeting this specific feature, which is the amount of the transaction. So basically we want to know if suddenly the amount is just going up in every transaction, something might be anomalous, so we set up different windows to check over time these amounts. So we have here 3 of them, one for with reference value, with a reference window, and with the this one is this is the simple one, just computing statistics. So if we go here on the right side, we can select the configurations that we saw below. So for example, I can go to the one with the reference value, and we will see here difference values already. You can set to check the difference, to just have a view from a different perspective on all the data that was all the results from the feature monitoring runs, let's say. So we can filter by time here, basically. And in this case, we see that all the values that were up over 500 are considered anomalous. So that's why we see this alert here, and we can navigate in time to see all the different executions of our monitoring setup. So if we have more computed here, we can select with different color. I'm not sure which one I have, but more values, not this one. But yeah, basically we can see different feature monitoring configurations at the same time, but of course only if the values, the x-axis and y-axis actually make sense, if they are in the same scale. Yeah, I think that's pretty much all. Then yeah, for every configuration you can either click disable to disable it. So then the schedule is basically disabled, and no, it will not be triggered in the next execution, or you can just, as we saw in the slides, call run once, so it will be trigger one time only, regardless the schedule. So the next execution time, the scheduler, it will be maintained, even though I just run it manually once. And then the last thing is the alerts. In this case, I don't have any alerts set up, but it's basically, you can go to the project settings here under alerts, and you can configure your different channels first, email, Slack. I don't have any webhook right now for the Slack channel, but you can basically provide your webhook, a specific channel name, and then if we go if we go back, we will have our channel configured, and we can set up receivers for the alerts, and they will basically appear here on our feature group. If we go here, add an alert, we can say, okay, notify me when one of the feature monitoring configurations applied to this feature group detects a shift in the data, or every case, let's say, even if it's not detected, I want to get a notification with a summary of the statistics that were computed and how was the analysis, how was the difference between the detection and the reference. So I think that I went a little bit fast, actually. That's pretty much all I had for now. So yeah, all right. So if there is any question for later, feel free to join our public Slack in public-hopsworks.slack.com and just drop any questions there. And yeah, thank you for listening.